Hello, good evening, students. Welcome back. And today, very important topic is before us. And that question will be there in the paper. Students, very important topic is coming. And we have discussed the mechanism of the nucleophilic substitution reactions. And one very important part of the nucleophilic substitution reaction is the stereochemical aspects. Stereochemical aspects, very important question will be coming in the paper. Very important questions will be coming in the paper, students. What I'm saying, stereochemical aspects. What it means? What it means? We are talking of that what is the stereochemistry of the products in the nucleophilic substitution reaction. What do you mean by stereochemistry of the product, students? You know, we have been telling you about certain isomers like structural isomers. And then we have mentioned you in 11th class also, stereoisomers. These are the isomers which have different arrangement of atoms or species in space. And in
Yes, sir.
that stereochemical aspects, one very important thing which we have to know is optical activity. Very important. What is optical activity, students? What is optical activity? Do you have any idea about it? You know what is optical active compound?
No, sir.
Okay. You see that it was found by Van 't Hoff and C. Lee Bell in 1874 that special arrangement of four groups around a central carbon is tetrahedral. And if all the substituents attached to carbon are different, that carbon becomes asymmetric, is known as stereocenter. There is no symmetry in the molecule, and it gives rise to optical activity in certain or in such organic compounds. Very important point. It was observed experimentally. You know that optical active compounds are those which can rotate the plane polarized light. Now we have to know what is plane polarized light. I am saying it was found experimentally by Van 't Hoff when carbon which is tetrahedral is attached to four different groups. They've observed that these compounds were optically active. I'm saying optically active means they were rotating the plane polarized light either towards clockwise direction or towards anti-clockwise direction. So we must learn first what is a plane polarized light. So I'm talking of second point here. What is a plane polarized light? You see that if there is an ordinary light, what it is what happens when there is an ordinary light, students. It in this the vibrations are taking place in all the directions. What is light? It is electromagnetic radiation, and vibration take place in all the directions. And if we if we pass ordinary light through a Nicol prism, what happens is the light becomes plane polarized. What I'm trying to say, supposing here is my ordinary light. I am showing this is a source of light. This is a source of light. It emits light in this form. Here you can see that
Yes,
there
sir.
are vibrations in all the directions, in all the directions. So
Directions.
when I pass it through a Nicol prism, what happens? What happens? I am getting this type of light. In this, what is happening? The light is vibrating only in one direction. One direction. You can see up and down. It is called plane polarized light. Plane polarized light is obtained. Ordinary light passed through a nickel prism gives rise to plane polarized light. And if this light is passed through, if I have a sample, here is my sample, students. Sample passed through in compound of carbon, in which I am saying carbon, how many groups are attached to carbon? 4. Okay? It is tetrahedral. Carbon is tetrahedral, 4 groups. And if 4 groups or 4 substituents which are attached are different, I am saying these are different groups, student. For example, one is A, other is D, E, F. 4 different groups are attached to the carbon. How many? 4 different. It can be CH3, supposing it is H, it is C2H5, and supposing it is Cl. Now 4 different groups are attached. Can you see?
Yes, sir.
Now here there are 4 different groups. What he observed, if plane polarized light is passed through them, they rotate the plane polarized light. How they rotate?
Yes, sir.
Either towards clockwise direction. This rotation is which side? Clockwise.
Yes, sir.
So they called it dextro. Small d. Or they said they found there is a mirror image of this.
Yes, sir.
Mirror image of this. If I put a mirror, how it will look like? That rotates the plane polarized light in the anti-clockwise direction.
Yes, sir.
What has happened? This light is rotated towards this direction. This is called laevo. So they observed such compounds are called optically active compounds. What do we call? Such compounds
Optically active.
Called optically active compounds. Is it clear?
Yes, sir.
And experimentally it was observed. Started the big thing about this, that oh my god, the compounds can rotate the plane polarized light. Therefore they started working on it. What is optical activity? What is the condition of optical activity? Especially what will happen when nucleophilic substitution reaction takes place by
Yes,
2
sir.
different mechanisms to the compounds which are optically active. So therefore, in this matter, we are going to learn about certain important definitions, terms which we are talking of. What we are talking of? Molecular asymmetry.
Okay, sir.
Molecular asymmetry.
Asymmetry.
What we want to learn, what is chirality, and what we want to learn, what are enantiomers, students. In the exam, direct definitions are also asked. What is molecular asymmetry? What is chirality? What are enantiomers? Such questions will be asked to us in the paper. Yes, but we understand what is the experiment which was done by Van Hoff and C.L. Bell 1874. They were able to observe optical active compounds. There is an instrument in which this was done, which is called polarimeter.
Yes, sir.
You have heard about polarimeter. So what we found, that there is something called polarimeter, students, that in that we can observe optical activity of the compounds. Let us see what are these definitions which we want to know. What we told you first of all, what is a symmetry? First, something is symmetric, supposing. What do you mean by symmetric? Supposing I draw a circle. It is a circle. You got?
Yes,
If I
sir.
cut it into two halves, it has a plane
Hmm.
of symmetry. It has a plane of symmetry. Okay? Equal
Yes,
halves
sir.
can be cut. Even if I use this point, this two equal halves. If I take a scale, this is a plane of symmetry. This is a plane of symmetry. These molecules, these figures are symmetric, students.
Yes, sir.
But supposing I take something like this. Now this is asymmetric.
Hmm.
This figure is asymmetric. You cannot cut it into two equal halves.
Okay, sir.
You cannot cut it into two equal halves.
Huh.
So what we are saying, asymmetric. When we will use this for organic compounds, in organic compounds we have carbon,
Yes, sir.
carbon. When carbon is attached to four different groups, students, I'm saying carbon attached to
4 different groups.
four different groups or species
Hmm.
or atoms.
Yes, sir.
Then that carbon is called asymmetric carbon. Asymmetric carbon.
Hmm.
And the molecule is called chiral.
Hmm.
Chiral means it is asymmetric. It does not have a plane of symmetry. It does not have a plane of symmetry. Chiral.
Okay, sir.
And if all the four groups are not different,
Hmm.
then molecule will become achiral.
Yes, sir.
Achiral. I have attached A. Chiral means four
Hmm.
different groups. Achiral means it does not have all the groups different.
Yes, sir.
So here we are saying if two groups are same or more than two groups are same,
Okay, sir.
that molecules become achiral. Achiral
Hmm.
means which is not asymmetric, which is not asymmetric. And it is observed the molecules which are chiral, they are optically active. Compound will be optically active if it has a chiral center.
Mm-hmm.
Molecule can have more than one chiral center also. In glucose,
Yes,
there are
sir.
more than one chiral carbons.
Huh.
So there are many optically active isomers of the glucose. Many, not one.
Okay, sir.
So we have to see if the molecule is chiral, then it will have a mirror image.
Yes, sir.
It will have a mirror image, students, which will be non-superimposable. Non-superimposable. And non-superimposable mirror image is known as enantiomers. So mixture containing anything which is chiral, which has a symmetric carbon, will have a mirror image which is non-superimposable. And this pair, the non-superimposable stereoisomer, they are stereoisomers because they differ in the position of groups in space. So non-superimposable pair, they are known as enantiomers. They are called enantiomers. For example, students, if I consider butan 2-ol, this is butan 2-ol.
Yes, sir.
You can draw the structure of this. I'll give you 1 minute. Okay. If you draw the structure of this
2 minutes, sir. I think. Going, sir.
butan 2-ol.
Done, sir.
Okay. Tell me, is there any chiral carbon in this? Is the molecule
In this,
chiral?
sir.
Is this molecule chiral? Does it has any carbon which is asymmetric? Butanol means what? How many carbons are there in butanol?
Sir, I think it is chiral, sir.
1, 2. This,
Yes, sir. Sir, it is chiral, sir.
this is butanol. Is it chiral?
Yes, sir.
Which
Yes,
carbon
sir.
which carbon is asymmetric?
Sir, center is chiral.
Give me the number of the carbon which is chiral.
Sir, the
How many
that
carbons
was-
it has? 1, 2, 3, 4.
Yes, sir, 4 carbons.
Which one is chiral carbon? Which carbon is asymmetric?
Sir, the third chiral, third.
Third. Give me the number. How you number the organic compounds?
Yes, sir. First would be CH3.
4 carbons. Then which carbon is that?
Sir, I think
Is the first carbon chiral? First question is this.
yes, sir. No, sir. Yes, sir. Yes, sir. This is chiral. Yes, sir.
Where is it chiral? How is it? How is asymmetric? I'm saying, is this carbon asymmetric?
Okay, fine. So this will be achiral, then 2, 3, and 4 will be chiral. Okay.
Huh?
Sir, this will be achiral, I think.
How many groups are there in this? The 3 hydrogens are there, so they are same. What about this?
Okay.
Carbon.
One hydrogen and 2, and one oxygen hydrogen.
How many groups are there? 4.
Yes, sir.
Which one? Hydrogen, this one, and this and this. So what is the story of this? How many groups are attached to this?
4.
CH3, and this is C2H5. So this carbon has got 4 different groups. Are the groups same? How many groups? 4 different. This carbon number 2 is asymmetric. This carbon is asymmetric. Yes or no? Carbon number 2 is asymmetric in butane 2-ol. Yes or no? Tell me.
Yes, sir.
Only this carbon is asymmetric. Why? There are 4 different groups attached to it.
Yes, sir.
Now what will happen then? If I draw the mirror image of this, here I have shown the mirror image of such a compound. This is my butane 2-ol. This is OH group. This is CH3H2H5. This is a 3-dimensional diagram of butane 2-ol. This is a dark wedge, dashed wedge. This is going away from me. This is in the plane, and the mirror image of this will look like this. D and E are mirror images. D and E are
Mirror images, sir.
Mirror images of each other. But they are non-superimposable. Non-superimposable, students. They are called enantiomers. What do we call them as?
Enantiomers.
Enantiomers. They are stereoisomers, which are mirror images of each other and non-superimposable. What is the definition of enantiomers? They have asked in the paper, what is enantiomer? What is our answer? Stereoisomers.
Sir, sir, they are mirror images, but they cannot superimpose.
They are stereoisomers, which are mirror images and non-superimposable. That's what I'm saying. What are they? Stereoisomers.
Which are mirror images, but can't superimpose.
Mirror images and non-superimposable. They are known as enantiomers.
Enantiomers, yes, sir.
And they will be optically active. If one compound is D, the other will be L. Means to say that if one rotates the plane polarized towards clockwise direction, other will rotate the plane polarized light towards anti-clockwise direction. So I don't know which is D, which is L. Only experimentally we can verify. Okay? After doing experiment in polarimeter, we will be able to find which is D and which is L. One will be dextro, other will be laevo. So which compounds will be optically active? What is the condition? Question was there. What is the condition for organic compounds to be optical active? The molecule should be chiral. At least one asymmetric carbon should be there. There can be more than one asymmetric carbon, as I told you. Then there will be more.
Okay, sir.
And there will be more optically active isomers. Clear? A question will be coming in the paper based on this.
Clear, sir. Clear, sir.
Okay. Now we will take some questions and examples first of all on this. We know what enantiomers are. These are enantiomers will have same physical properties like melting point, boiling point, solubility, refractive index. The only difference will be in the direction of the rotation of plane polarized light. Okay? What I'm saying, enantiomers have same physical properties. Enantiomers have same enantiomers. They have same physical properties like melting point, boiling point, solubility, refractive index, same. What is different? Tell me what is the difference in enantiomers? All the physical properties are same. Then what is different? One rotates the plane.
Sir, they can't superimpose.
How will I know experimentally what I am talking about?
Sir, optically active.
They differ in the rotation of the plane polarized light.
Okay, yes, sir, yes.
What is we have to write it? What I am saying, rotation of plane polarized light. They differ where? Only in this. Experimentally, how will I know? They will be rotating plane polarized light in different directions. And that is what we say they are mixtures. What we say they are enantiomers. What they are? Enantiomers, students. Clear? Tell me.
Yes, sir.
Okay, let me rub this and get some more space. Optical activity, very important questions are coming in the paper. One question will be there every time. We must understand it very clearly.
Hello.
Now we are coming to more important points. Yes, what is the more important point? We have told you what are enantiomers, what are optical active compounds. This we have learned. What are optical active compounds? Now, for example, they gave you questions like this. You say 2-chlorobutane. ठीक है? 2,3-dihydroxypropanol. Propanol. Butan 1 all. Question. Which are chiral? Which are chiral molecules? Question. Which are chiral molecules? We are given 3 compounds. 1, 2, and 3. Tell me, you have only 1 minute.
Hello.
Hello.
Yes, sir. Yes, fine now. Fine now.
Okay.
Yes, sir.
Which is optically active, which is has a chiral molecule? First, 2-chlorobutane. What is the structure of 2-chlorobutane? 1, 2, 3, 4. This is 2-chlorobutane. Is it chiral? What is 2,3-dihydroxypropanol? 1, 2, 3 propanol.
Yes, sir.
2, 3 dihydroxy. What is this group? H. Okay. Tell me, what is butan 1 whole? 1, 2. Tell me, which is first one? Is it chiral?
Chiral. Yes, sir. I think so.
Which carbon is chiral?
Sir, the second carbon, I think.
1,
Not
2,
sure.
3, 4. This carbon has got 4 different groups.
Yes, sir.
This is chiral.
Yes,
What about
sir.
this?
Sir, I'm not sure. I don't think this is chiral.
3. Carbon number 2. How many groups are there? 1, 2,
3, 4.
3. Are they same? These 4 groups same or different?
I'm sure they're different, sir.
Then this is chiral.
Okay, sir.
What about this? 1, 2, 3, 4.
3, 4.
These 2 hydrogens same, 2 hydrogens same, 2 hydrogen, 3 hydrogens same. This is achiral. I said achiral. We have to identify in the paper what is chiral and achiral molecule. Then we have to see there could be any carbon which is asymmetric. What is asymmetric carbon? When 4 different groups are attached to a carbon, that is clear. Any doubt?
Yes, sir. No, sir.
Okay. Now what we are talking, we said there are enantiomers. And one is D, other is L, dextro or laevo. If it rotates plane towards clockwise direction, we say plus. And if it rotates in anti-clockwise, we say minus. So we can say there is a plus and there is a minus. How do you measure? By polarimeter. If I have 50-50 mixture of enantiomers.
Yes, sir.
What will happen? and 50-50 mixture of enantiomers, what will happen? Then I can say it is DL or plus minus. Plus minus means 50, 50 plus 50 minus. Then what will be the net optical rotation? What will be the net optical rotation? 50 plus 50 minus, what it will become? 0. Such mixtures are known as racemic mixtures.
Yes, sir.
What do you call that? Racemic mixture or racemic modification. What do we call them? Racemic modification. So he will ask you in the exam, what is a racemic mixture? What is your answer? One, I define enantiomers. Second, I define 50-50 mixture of enantiomers. What is that known as? 50-50 mixture of enantiomer is known as what? Racemic mixture.
I don't.
Racemic.
Okay, sir. Racemic mixture.
Note it down. Note it down. Then I will rub it. Note down everything.
Copying, sir. 2 minutes, sir.
Okay. Note it down. 1 minute.
Done, sir.
हो गया?
Yes, done, sir. Done, sir.
You have noted down?
Done, sir. Yes, sir. Done, sir. Noted down.
Okay. Okay. Note it down. Now the question was given in the paper. What question was given? Identify the chiral and achiral molecules in each of the following pair. Student, question number 1. You are given this pair. Tell me which is chiral and which is achiral. Similarly, this pair, which is chiral and achiral. Similarly, this, which is chiral and achiral. You have 1 minute to answer the question, students. Identify the chiral and achiral molecules. Question number, first part. This compound is chiral or achiral? This one. Where is the carbon? This one. How many groups? 1, 2, 3, 4. Are the 4 groups same or different?
Different, sir.
Then what is it? Chiral or achiral?
Chiral, chiral.
Chiral. Okay. What about this? How many groups? 4. This is the carbon. Then tell me, these groups are different or there are any same groups? This group is same. This is same.
Hmm.
Then chiral or achiral?
Chiral, sir. Achiral.
A.
Same.
These two are same. What about this?
This is sir. Sir, this is chiral.
This carbon has OH, He, and this.
Yes, sir. Chiral, sir. All different.
This point. Chiral. What about this?
Sir, this is achiral.
You can cut this
Same.
two equal halves. Same.
Yes, sir.
Achiral. This question was given in the paper. What about this? One question will be there in the exam based on chiral and achiral carbon. What about this?
Sir, sir, this is also chiral.
Which carbon?
So the second carbon, yes, this one.
What about this?
So this is also a chiral. Chiral.
Achiral. So questions are coming in the paper like this. Identify the chiral or achiral carbon. Now, important thing is that you are saying in our nucleophilic substitution reaction. I told you two mechanisms, SN2 and SN1. In SN2, what happened? What was happening in SN2, students? If this was my X, the nucleophile was coming from the back side. And this was leaving. This was leaving. So what was the result of that? What is the result of that? If something is like this, then what is happening? As you can see, the OH group comes from the back, the leaving group leaves from the other side. What will be the result of that, students? This is pointing towards me and this group is going away from me, then what will happen? What will happen in this case? This is pointing and this group is going away from me. What is the result of this? You can see that there is an inversion of configuration. What I'm trying to show? Inversion of configuration takes place in SN2 mechanism.
Yes, sir.
If the carbon is chiral, if this molecule is, what I'm saying, if this carbon attached to the X is asymmetric, I'm saying now, asymmetric, then the result will be inversion of the configuration. Okay? If it is a D,
yes, sir,
then the product will be L. Dextro to laevo. Plus will become minus.
Yes, sir.
This will be the result in the case of carbon which is asymmetric and undergoing SN2 reaction. Yes or no?
Yes, sir. Yes, sir.
In SN1, what happens? SN1 proceeds to formation of a carbocation. Carbocation. What is carbocation? You have seen. This is a carbocation. This is a carbocation. And if this carbon, supposing this carbon is asymmetric, then what is going to happen? Supposing I put C3H7. If this carbon is asymmetric, now this is a flat molecule, planar molecule, planar 120 degree in the plane of the paper. What happens? The attack can take place of the nucleophile.
Okay, sir.
50% from the top and 50% from the bottom.
Bottom. Yes, sir.
So what will happen? You will get 50-50 mixture of 50-50 mixture of DL. And what will be the result? You will get a racemic mixture. What you will get? Racemic mixture or racemic modification.
Yes, sir.
And the compound will be optically, what will be the result? What you are getting 50% of dextro, 50% of the laevo, the net result will be zero optical rotation.
Yes, sir.
But you will obtain. So this is called racimization. Racimization, and the product is optically inactive.
Okay, sir.
In that case, in the first case, product is optically active, but inversion of the configuration takes place. And if the carbon is not asymmetric, then there is no problem, nothing will happen. Because carbon is not asymmetric, then it can be said that retention of configuration. So there are three things only. What? Inversion, retention, and racimization. So SN1 you are saying racimization, SN2 you are saying inversion. And if the carbon is not asymmetric, then there is no change. And then we can say that there is a retention of the configuration during the nucleophilic substitution reaction. So three possibilities are there when a nucleophilic substitution reaction takes place. Right? This is an important question has been asked in the papers.
Okay, sir.
This is an important question. There can be questions on optical activities are usually asked in the exam students. For example, SN2, SN1 questions will be there in the exams. They will ask you questions based on this. For example, in SN1 and SN2 type of questions which have been asked, SN2 and SN1 questions are important for the exams.
Yes, sir.
Here, a question has been given. Which alkyl halide would you expect to react rapidly in SN2 mechanism? Explain your answer. There, SN2 mechanism. This or this, which is faster in SN2?
This one, sir.
Which one? What is the order of reactivity of SN2?
SN2, sir, 1 degree, 2 degree, 3 degree.
Order of reactivity should be known to us.
Sir, 1 degree, 2 degree, 3 degree.
1 degree, 2 degree, and 3 degree.
3 degree.
Then which is faster? This one or this one?
Sir, this one, first one.
First one is faster.
Yes, sir.
This is 1 degree. This is 2 degree.
2 degree, yes, sir.
And now the question is which is chiral? This one or this one?
Sir, sir, both are chiral, I think.
Both are.
No. Sir, second is chiral.
This one is chiral.
Yes, sir.
This carbon.
Yes, sir. This is chiral.
Now, out of this and this, which will be faster?
Sir, first one will be faster. It's 2 degree.
This
the first one. Yes, sir.
This is faster. Which is chiral?
Chiral, sir. Chiral. Sir, second is achiral, first is chiral.
This is chiral.
Yes, sir.
This is achiral. Therefore, questions can be put in any way. If
Yes,
I come to this question, students, out of this, which is faster SN2 and which is chiral and which is achiral? The question here is which are chiral and achiral? Identify. They will ask you question in the paper like this. Identify. So what is the answer coming out of these two? Which will be faster?
Sir, I didn't hear you, sir, too much. Can you repeat once? Yes, sir. Out of these two, sir, both are, wait. Sir, first is faster.
Huh?
The first is
This
faster.
is faster.
Yes, sir.
This is faster. Which are chiral?
Chiral. Sir, first is chiral. No, wait.
Both chiral. This
Yes, sir.
carbon.
Sir, both are chiral, sir.
Chiral.
Yes, sir. Sir, both are chiral.
Chiral. Okay.
Yes, sir.
Next question. In which of the following, which is faster and which is chiral and achiral? Identify chiral and achiral also. Chiral. Out of these two, which is faster for SN1 is saying. SN1. What is the reactivity order in SN1?
So 3 degree, 2 degree, 1 degree.
Okay, then identify. This
Yes,
is
sir.
faster or this is faster?
Sir, out of these 3 degree. Sir, first is faster, second is slower.
Which is chiral?
Sir, both are chiral, I think.
Chiral. How?
No, sir, both are achiral. Both are achiral. Both are achiral. Both same.
Same group, same group, same group.
Yes, sir, both are achiral.
Achiral. Achiral. What about this? Which is faster?
Sir, out of these, sir, first is faster.
This is faster than this. Which is chiral?
Sir, second is chiral.
This is chiral.
Yes, I think it's chiral because C and yes, sir.
How?
Yes, sir, it will be chiral because sir, C one side and Cl one side.
What C? This is where is the chiral carbon here?
Sir, the first carbon is chiral, I think.
Where this is hydrogen, 2 hydrogens are attached here. 2 hydrogens, 2 hydrogen, 2 hydrogen. CH.
Okay, fine.
Then,
okay, fine. Yes, sir. Yes, so both are achiral.
What about this?
So which one?
This one.
Yes, sir. This is also achiral.
How?
So because C and C,
Carbon.
carbon.
This is CH3, this is carbon, this is Cl, and this group is there, and there is a hydrogen.
Yes, sir. Yes, sir.
Then what is this carbon?
Achiral. Yes, sir.
What is this? Chiral. 4 different groups. This group is not the same as this ClH. Then these groups are different.
Yes, sir. Yes, sir.
What is this? Chiral or achiral?
So which one?
This compound.
Sir, this is chiral.
All right. So now I think you have been able to learn. One question will be coming based on this. What is optical activity? What are enantiomers? What is racemic modification? What happens in SN2? There was a question last year. Inversion of configuration will take place. What happens in SN1? Racimisation will take place. And how to identify chiral and achiral molecules. Can you do all this now? Or any doubt is there?
No, sir. I'm clear now.
Okay, that ends this part, which is the stereochemical aspects. One question will come in the paper on this. Therefore, we will continue in our next class further on these properties and other type of reactions of haloalkanes and haloarenes.
Yes, sir.
Okay, then you have noted down everything?
Yes, sir.
All right. Good night. We'll see you in the next class.
Okay. Good night, sir.
Good night.